Hi everyone. In the quiz, I had asked you to calculate the area of a circle using either polar coordinates or symmetry with integrals. And what many of you have done in class was, let's say if I have a circle over here, you know that the circle equation is given by x square plus y square is radius square. Let's say the radius was a. Now many of you have done it correctly and said that, okay, what we're going to do is we're going to take a small section, let's call this dx, and related to that small section now I have a small differential area over here. If this is y prime, then the small differential area dA is going to be given by y prime times dx, and y prime is going to be, if I am some x away, y prime is going to be a square minus x square, the square root of that. So you have tried to calculate the area. You're saying that the differential area, this d is not the derivative, but this basically is saying a small section of the area and then what you're basically saying is, okay, if I integrate from x is equal to 0 to x is equal to a, if I integrate this d area, if I integrate this d area or the differential area from x is equal to 0 to x is equal to a, I should get the area of this quadrant, and if I multiply by 4 I should get the total area of the circle. That's all right. So you're basically saying area of the circle is going to be 4 times x is equal to 0, x is equal to a square minus x square dx, and that's the integral you have to now evaluate. There are many ways you can evaluate this integral. You can use substitutions. X is some a sine theta, and then convert the integral form there. But my question to you is this now. Is this the best way of calculating something which looks like a circle? Yes, you will get to the right answer if you do this integral, and many of you did get to the right answer. But is this the most elegant way of solving this problem? What you have done here is you have made your life easy in the xy coordinates. You haven't really needed to think here, but now you have ended up looking like with an integral which is now slightly more difficult to solve. And this is just a circle. Now if I said to you, okay, now calculate me the volume of a sphere, which is a three-dimensional object, you will end up into a problem very, very quickly if we start using the same method. So while this is correct, it's not really a good engineering way of doing things. And so the question now comes is, how do I solve this? What would the best way be? And you have done polar coordinates in your class, in your maths course before. And if I ask you, you have done polar coordinates before, and now let's try to understand what those polar coordinates are, and then let's try to pick up a differential element in those polar coordinates and see whether we can calculate the area of a circle easily with that case. Now if I went and asked you, if I send you back to your high schools or even elementary schools and I ask, go and draw me a circle, would you have drawn the circle the way you are integrating here? In that I would draw one line like this, and then I'll go a little bit forward and draw a line like that, and then figure out here and then connect those lines? Obviously not, right? What would you do if I was asking you to draw a circle in your high schools or elementary schools? What would you do? You would take a compass you would adjust the, first what would you do? You would take this compass and you would adjust its length so that you get to the radius. Once you have fixed the radius, you will now move this around to make your circle. So you would take this point and you would push this point, as my finger is saying, showing you, you would push this point 90 degrees to this radius point and move it around. While you're moving this around, you're not adjusting the radius at all, and when you are adjusting the radius, you're not doing anything to that point. So you would do two steps, right? You did two steps here when you were drawing circles in your elementary school. The first step would take and push it forward, and the next step would apply a force of 90 degrees around this, or torque if you want to use ECE 105 concepts. You would apply a force of 90 degrees around this and then move this in a circular fashion. That's exactly what polar coordinates are doing. So if you now see, what am I doing in polar coordinates? If I have, let's say this is X, this is Y direction. What are you doing in polar coordinates? You have one vector which is taking an element from here and is pushing it forward. So you have one vector here which is going from the center and is pushing it around, is pushing this forward, as you took this compass and then you basically had, as if I'm applying a force towards this direction, and with whatever radius I want to go to, I'm pushing it forward. And that's what I'm going to call vector R. And let's call this to be distance R away. That's the radius you've chosen. And there is another vector which is taking the angle you're making, and by very definition we define this angle with respect to the x-axis, and you're putting a force which is 90 degrees to that, and you're calling it vector phi. I believe when you were doing polar coordinates, they did rho and theta. In your maths course, probably they used rho and theta as the terms. I'm going to use R and unit vector R and phi. And the reason I'm going to use this is because once we go to spherical systems, that is the convention which is used. So I can extend this to a spherical system very, very quickly without having to change my nomenclature. So basically this polar coordinate system is defined by a vector which is a radial vector, and that vector is, what that vector is doing is what you were doing with your compass, taking and pulling it outwards. So as I'm doing this is the job of this radial vector, and I can adjust the distance from the center using this radial vector. And the other vector phi is what we call the azimuthal vector. And what that is doing is taking your adjusted radius and then rotating it at about the center. Exactly like you build circles with compasses in your in your high schools. So this becomes my polar coordinate system. Let's now see how we can define, let's go back to the problem of calculating the area of a circle and how we can use this polar coordinate system to calculate that area very, very easily and very, very quickly. So again, I have my vector x and y. I have an area of the circle, and obviously as I go to different points, the effective area is changing. So I have to do an integral. To do the integral, I have to find a differential area element such that if I take this differential area element, this small baby area element, and I integrate it over my whole space, then I should be able to calculate the area of the circle. So let's say I go to a point, some point here. I go to this point and I want to define the differential area around that region. I'm going to say this point, I'm going to define this point now based on my vectors. So I'm going to say this point is at an angle phi with the x-axis, the azimuthal angle is phi, and is at a distance r from the center, some arbitrary variable I have put in, the radial variable I have put in. Now to make an area, so I'm already sitting here, I'm basically sitting here, that's my point. Now what I need to do is I need to define, I want to move in r and phi. This vector system which I have now created, again remember this was when you were in x and y, you were moving either in x direction or in y direction. The Manhattan grid system, for example, you are either moving in x or y, and you are trying to define all your problem based on that. Now I want to use this polar coordinates, and I want to either move in r direction or in phi direction. These are the only two directions I want to move in, and I want to be able to define my differential area based on these two directions. So to do that, the first thing I will do obviously is take this and move this forward a little bit. So I create one width like that. So I move it a little bit forward. That becomes moving in the r direction. So I'm moving it a little bit forward in r direction, differentially in r direction, dr. And then, so that becomes one side of my area. And then, because I have to move in phi direction, I'll just move it little bit in angle over here. So originally I was at that point, and again I want to use this coordinate, so I can only move in r direction or phi direction. So I moved it a little bit in r direction, and then I'll move it a little bit in phi direction. So I go from that point to a point above, and I have a small angle change which is d phi, and thus my differential element becomes this shaded part. This becomes my d area. Agreed? That shaded part becomes, so one small movement in r direction, one small change of angle, which we are calling it d phi. What would my d area be now? My d area is going to be this length multiplied by this length. Again, if I am assuming this is really small, I can assume that to be a nearly rectangular shape. If all these changes are really small, then this differential area element is going to be this width multiplied by this length, and that length is nothing but the arc length. That length is nothing but the arc length of that arc, and the arc length is the radius multiplied by the angle, so that is r d phi. So my d area becomes dr multiplied by r d phi. That is the differential area I get. Now what I have to do, I have to integrate this over the whole area of the circle to be able to calculate my solution. So my integral has to be some r dr d phi over the whole area of the circle. Now this looks like a complex integral, but it actually is not, because when you're moving in r direction, nothing is changing in phi. When you're moving in phi direction, nothing is changing in r. This is opposite of what is happening here. When you're moving in x direction, y direction is changing. The y length is changing around too. So this integral is not that complex to look at, as we will see very, very quickly. So what should the limits of this integral be now? Now what am I doing? How am I making that circle, or how am I making that disk? I have a circle. I go to a small point. I make a disk there. Then I move this point further and I make a disk again. I move this point further and I make the disk again. I move this further and I make the disk again. And as I keep on going, I would be able to fill this whole circle inside. So it's telling you my r has to go from 0 to a. I go to one point and then I change my phi from 0 to 2 pi. Then I go to another point, I change my phi from 0 to 2 pi. So the radius has to go from, I have to start from here, and every single point I have to go and make that circle. And as I keep on making that circle, I keep on filling inside, and thus I should be able to calculate the area. So the circle has to go from, the radius has to go from 0 to a, and my phi has to go from 0 to 2 pi. Just that, right? So my total area of the circle is going to be from 0 to r dr, and 0 to 2 pi d phi. So that just becomes, or 0 to a r dr and 0 to pi d phi. So that just becomes now a square by 2 into 2 pi, or pi a square. The maths became so much easier. That's the polar coordinates for you, and that's how you could possibly do it. You could have also done this question without having to write a differential area element, though I would suggest you should definitely learn how to do this, because a lot of questions, when you apply this differential elements, if you apply this the coordinate system to the symmetry of the problem, your integrals will become very, very easy. Your life would be much, much easier that way. But for this question, to calculate the area, you could have also done, you would have said, hey, I can look at the symmetry of the problem, and to me it looks like that if I was making a differential element, I can make a differential element which is a small ring like that. Every point here is the same point here, is the same point here, is the same point here. The area at any of these points would exactly be the same. So the symmetry of the problem tells me that I could have made a small ring which is a certain thickness to it, dr, is at a radius r away, and thus dA would be the circumference multiplied by the thickness. So that would be 2 pi r dr, and I have to integrate this from r is equal to 0 to a, 0 to a. Now you notice what you just did here is exactly what you had basically done with the full maths. You basically had seen that nothing is changing in phi direction, things are not changing around in phi direction. So because things are not changing in phi direction, the integral in the phi direction is just going to be 2 pi, and then all you have to do is an integral of r dr. So both ways, and obviously you should get the same answer, otherwise you're wrong, but you can possibly do it this way too. So again, remember, when you look at a problem, if the problem has a circular symmetry, then using xy coordinates does not help you, is not the elegant way to do it. You should go to polar coordinates if the problem has a circular symmetry. So the message is now again, so this is the take home message, the summary. For circular symmetry, use polar coordinates and in polar coordinates basically what you're going to have is an element which is dr, a small variation in r, and r d phi. If instead of asking you to calculate the area of the circle, I'd ask you to calculate the circumference of the circle, then all you're going to do is integrate this when r is equal to a times d phi, integral of that from 0 to 2 pi. But that is your element you're going to get. We'll have lots of problems with circular symmetry when we start calculating electric fields. So please get used to using polar coordinates.